All right, so welcome everybody to today's IAMP One World Mathematical Physics seminar. It's a great pleasure to have Pierre Germain today as our speaker from NYU Courant Institute. And Pierre will tell us about the kinetic wave equation and its derivation. So let me say that as usual, the seminar will be recorded and it will then be made available on YouTube. And I'm very happy to leave the floor to Pierre.
Thank you, and thank you for the introduction. Thank you for your invitation and the opportunity to give a talk here today. So in this talk, I will present the kinetic wave equation, but I will try to give a very broad perspective and try to convince you that it's an interesting equation. And there has been a lot of activity, a lot of work on this equation lately, so I will recapitulate what it's known as far as the derivation of this equation goes. And if time permits, but probably it won't permit much, I will give you some ideas of the proofs and the techniques involved. Yes, right. So here's the table of contents. So first, I will recall a few things about the most classical object in nonlinear kinetic theory, the Boltzmann equation. Then I will present two interesting questions on nonlinear dispersive or wave equations, whose answer might be related to the kinetic wave equation that I will present afterwards. And then I will tell you what's known about its rigorous derivation, and as I said, maybe even some ideas of the proofs. So one thing that's interesting about this equation is that it's related to many different topics. Of course, nonlinear kinetic theory. It's describing nonlinear Hamiltonian systems or nonlinear dispersive equations in a certain regime, which is known as weakly turbulent. And so that's the third connection to turbulence, which is the most interesting and the most intriguing. So turbulence, often looks like something completely out of reach to mathematicians and physicists alike. But in this specific context, I think the kinetic wave equation might give sort of an entry point into this set of problems. Okay, so let me start with the Boltzmann equation. Just recall a few things about this fundamental model that will, help us make sense of the kinetic wave equation. And of course, this is Ludwig Boltzmann on the picture. So as you know, the Boltzmann equation arises from Newtonian dynamics. So the dynamics of n classical particles that only interact by collisions that are elastic. The exact microscopic features of the collisions will play ultimately a role, but are not so important. What's important is that they're elastic, so that the energy is conserved in the collisions. So you look at this very classical system. There are n particles that collide each other like billiard balls. And if you take the Boltzmann grad limit, so this is a specific scaling limit where n, the number of particles, goes to infinity, epsilon, the diameter of the particles, goes to 0, and n times epsilon squared goes to a constant. So in this specific limit, if you define the density function as the function in phase space, so in the space x, that is the position, and v, that is the velocity of the particle. If you define this density function as recording the number of particles or the density of particles that have position x and velocity v at a given time t, Then in the Boltzmann grad limit, you can show that this density function converges to a solution of the Boltzmann equation that I now write. So it's a function, it's an equation on an unknown function that depends on the time t, the position x, and the velocity v. And once again, it's a density. It describes the density of particles that have these features. And so it has a linear part, which is sometimes called the Liouville equation, and which simply describes free transport. So what happens to the particle as long as they don't collide or see each other. And then there is a nonlinear term, which is called the collision term, which records the effect of the collision between particles. So usually it's not written in this way, but for the purpose of this talk, it's helpful to write the collision term as this integral. So it's an integral that has two delta functions. So this is to be understood in the sense of distributions. And these two delta functions record the two important conservation laws. So you see that V1, V2, V1 prime, V2 prime, which are the, well, yeah, I should say that first. So in this integral term, you have V1 and V2. You should think of them as the pre-collision velocities. So that these are the incoming particles. They have velocities V1 and V2. And then V1 prime and V2 prime are the post-collision particles, the post-collision velocities. So these are the velocities of the particles after they undergo a collision. And since the collisions are elastic, you conserve the momentum. So V1 plus V2 minus V1 prime minus V2 prime has to be 0. And you also conserve energy. V squared plus V2 squared minus V1 prime squared minus V2 prime squared also has to be 0. And this is recorded by these two delta functions that are, once again, understood in the sense of distributions. Right. Oh, well, let me repeat once again. So that's the collision operator. And there is these two important conservation laws, conservation of momentum and conservation of mass. So, you know, of course, this equation was put forward by Boltzmann. It was the source of much controversy, not the least because Boltzmann's equation is not time reversible, while the original dynamics is. So that's one of the paradox that you encounter. So mathematically, the rigorous derivation of the Boltzmann equation from the Newtonian n-body problem was first proved by Lanford in the 70s in a proof that had some lack of precision. And so more recently, Gallagher, Saint-Raymond, and Texier put forward a more complete proof of this derivation. So that's Newtonian n-body problem to Boltzmann equation. And the other interesting limit is to go from the Boltzmann equation to fluid mechanics, so Euler or Navier-Stokes. And this is so two important works are Goltz, Saint-Raymond for weak solutions and Yan-Guo for strong solutions.
Sorry, Pierre, just one question from the audience. The scaling you described, that's specific for 3-dimension, right? So
oh, yes,
we're specifying, we're in 3-dimension.
Yes, yeah. So the scaling, another way to put it is that the average number of collisions per unit time is 1 or order 1.
Okay, thanks.
So there are open questions, you know, is this indeed the only possible scaling, or are there other scalings in which the limit is valid? And another question is about, you know, the time scales over which these derivations can be established. So in this respect, there has been no progress since Lanford's paper. So what the timescale you can reach corresponds to an average number of collision, which is smaller than 1. And it's been very hard to improve on that. And finally, there is the question of quantum particles. So if you replace these classical particles by quantum particles, so there are several versions. Can you also prove that this an analogous collisional limit holds? So of course, physicists already came up with equations, and now it's up to us mathematicians to prove that they are true. What's interesting is that this quantum Boltzmann, so once again, there are many versions, these quantum Boltzmann equations are very much related to the kinetic wave equation that will be the subject of this talk. Okay, so that's what I wanted to say about the Boltzmann equation. But once again, it's the fundamental example that we will have in mind when thinking of the kinetic wave equation that I will present shortly. So one way to put it is that the kinetic wave equation replaces classical particles by linear waves, and the collision of classical particles corresponds to nonlinear interactions between linear waves. So this would be the analogy.
Sorry, Pierre, another question. In the non-quantum case, are the particles distinguishable?
Yes.
Okay. Okay. Yeah.
Okay, so now let me say a few words about nonlinear dispersive equations, which is where I come from, and where many open questions, where several open questions are related to, perhaps related to these kinetic descriptions. And so this little picture is meant to give an idea of the sort of system we look at. It's nonlinear waves that live on a compact domain and that keep on interacting with each other, and you like to understand the effect of it on the long run. So the simplest model that we will adopt for this whole presentation is the nonlinear Schrodinger equation set on the torus. So U is complex valued. You can choose the sign plus or minus depending on whether you look at the focusing or defocusing case, but it will not matter for what we want to do here. And the space variable lives on the torus, which is, if you want a compact setting, it's the simplest possible setup, because on the torus you have Fourier series, and Fourier series are very helpful to describe the linear Schrodinger equation. So I think that's the simplest model, but pretty much all I'm going to say should hold for other nonlinear wave models. So you pick your favorite equation, maybe surface on the surface of waves on the surface of water, or plasmas, or sorry. So any nonlinear wave model or any infinite dimensional Hamiltonian system should pretty much fit into the framework I'm going to describe. But for now, we stick to the nonlinear Schrodinger equation, and the question of its local and global well-posedness has been understood for some time. So local well-posedness in the sub-Bolev scale, optimal results on the local well-posedness in the sub-Bolev scale were obtained by Bourgain. And if you combine this local well-posedness with the conserved quantities of the equation, which are the mass or L2 norm and the energy or Hamiltonian, what you can obtain as usual is global well-posedness. So at least in dimension 2 or 3, and at least in the defocusing case. But so at least in some situations, we know that we have a global solution that is in H1 and that does not develop singularities. So it looks like this gives a very good understanding of the system. However, the next question, which I will call question 1, is to ask what is the qualitative behavior of U for large time, right? We know U does not develop singularities, and it remains bounded in H1. But what happens to it? If I look at time, 1 billion, what does the solution look like? What was the effect of these repeated nonlinear interactions? And of course, this should be asked for generic solutions, because you can always find exceptional solutions that are, for instance, periodic in time. The expectation is that under the effect of these nonlinear interactions, the energy or the Hamiltonian is transferred to high frequencies or small scale in a chaotic manner. And this process is often referred to as weak turbulence or wave turbulence. And of course, what it shares with regular hydrodynamic turbulence is this chaoticity of the nonlinear interactions. So that's a bit of a vague question. There is a more specific version of this question that is due to Bourgain. And that can be phrased in terms of Sobolev norm growth. So one way of, as I was saying, the expectation is that energy is transferred to high frequencies. So one way of tracking that is to control Sobolev norms with a high index of regularity. So for instance, if you control the H10 norm, it gives you a good idea of whether energy has been moving to small scales. So one interesting question is to understand the behavior of the HS, say, you can think of S being, I don't know, 100, H100 norm of a solution U of the nonlinear Schrodinger equation. So there has been upper bounds that were proved first by Bourgain, then improved by Stafilani, and then many others, that say that this Sobolev norms can grow only polynomially. So that's for upper bounds. And then there are lower bounds. The best result is due to Colliander, Kiel, Stafilani, Takaoka, and Tao. And these authors prove that if you give me a small number lambda and a big number m, then I can find a solution that in the HS topology goes from lambda to m in finite time. But the time it takes is exceedingly long, and we don't know what happens after that time. Then maybe it could go back to being very small in the H100 topology. So a question that was asked by Bourgain is, can you find a single solution, U, whose H100 norm goes to infinity as t goes to infinity? To put it in more physical terms, can you find a single solution that does what it's expected to do, namely transfer its energy to high frequencies as time goes by? And this question is for now completely open. And of course, that's very disappointing, because this is something that should happen for, in a way, almost all solutions. but we're not able of finding a single one that does that. So that's question one. And this corresponds to the setup where you let the system evolve from given data, and the expectation that it will transition to some turbulent behavior, even if initially the data was very tame. Another possible setup is to force randomly the system. So that's the most classical setup for hydrodynamic turbulence, and also it's physically very relevant. There are many systems in which you have this forcing that happens at large scales and dissipation that happens at small scales. So in fluids, it's maybe you shake the system at scale 1, and then viscosity will dissipate energy at very small scale. So you can the same is true for many wave systems, in the atmosphere, in plasmas, in many setups. So in the framework of the nonlinear Schrodinger equation, it means you take the nonlinear Schrodinger equation, you force it at low frequency, and you dissipate it at high frequency. And you force it in a random manner. Then this is not hard to show that there is an invariant measure. And for instance, Cooksin was one of the first to consider this question. But what's very hard is to say anything specific, quantitative about this invariant measure. And what you see in experiments, so here is a typical picture that you find in physics papers. What you see in experiments is that so here, this is where the system is forced, and this is where the system is dissipated. And in between, you have a certain slope so that it's in a log-log scale, and it tells you how much energy lives on a given frequency range. You have a certain slope, and what physicists would like to do is to be able to explain why you find this this slope or this power law. And this has proved a very, very hard question. So question 1 is about the large time behavior of the unforced system, and question 2 is about understanding the power law in such a forced dissipated system.
Sorry, and what is in the plot? What is I eta k? I missed that part, sorry.
Yes, so I eta is a density of energy, and k is the frequency range. So you see that what you do is you input energy at frequency around 20, right? And then it trickles down along different frequency ranges, right, through the nonlinear interaction that enables the energy to go from one scale to another. And then when it reaches a high enough frequency or a small enough scale, it gets dissipated. Right? But the question is, this sort of transport mechanism of energy through scales by the nonlinearity, can you understand it? And a way of framing the question is, can you explain why you find this specific slope?
Okay, thanks.
Okay, so now I'm going to present the kinetic wave equation, and I will try to argue that it can help answering these questions. And so the two persons you see here are on the left, Pierre, who was a German and then later British physicist, who was the first to write down the equation. And on the right, Vladimir Zakharov, who was the main figure in reviving this whole theory. So Pierre was more interested in solid state physics, and Zakharov was more interested in nonlinear physics, fluid mechanics, this sort of things. So the regime that physicists favor is called the weakly turbulent regime. So that's the nonlinear Schrodinger equation that I wrote down earlier, but now I added two parameters. One is lambda, that quantifies the strength of the nonlinearity, and the other is L, that quantifies the size of the domain. And the weakly turbulent regime in which the kinetic wave equation should be valid is the one where the nonlinearity goes to 0, so lambda goes to 0, while the volume becomes infinite, or equivalently, if you rescale things and if you fix the domain to be the unit torus, then what you're asking is that the system is moving towards high frequencies. So these are the two most easily understood assumptions. So weak nonlinearity and infinite volume. Then here comes the more complicated one, the random phase approximation. This is saying that if you look at the Fourier modes of the solution, and if you look at the phases of these Fourier modes, then the phases are IID random variables. And of course, physicists usually take this for granted, but that's very hard from a mathematical viewpoint to understand how this can be propagated, because of course correlations will occur through nonlinear interactions, and the whole question is to quantify these correlations. So this regime, well, first it's interesting because it will enable us to derive the kinetic wave equation, but also that's a physically relevant one. That's the system in which the systems for which I asked the questions 1 and question 2 correspond to this regime. So that's a relevant regime. So here is the physicist prediction. You take the solution U, you expand it in Fourier modes or in Fourier series. You consider the weakly turbulent regime, and then you look at the expectation of the kth Fourier mode. Then this, so because of course you're looking at an ensemble of solutions, right? The fact that the solution is the phases of the Fourier coefficients are IID means that you are considering an ensemble of solutions. Then if you take the expectation with respect to this randomness, this converges to a solution rho of the kinetic wave equation. And as for the frequency parameter k, remember the physical space is the torus of size L. So the frequency, the dual frequency space will be ZD over L. And as L goes to infinity, in a natural way, you converge to a continuous frequency variable in RD. And so here is the kinetic wave equation. So it's, you should think of it as a version of the, or as a parent of the Boltzmann equation. And there is a dependence in X that I did not write, but everything depends on X. So on the left-hand side, you have Liouville's equation that corresponds to free transport. And on the right-hand side, you have a collision operator that is very similar to the one we saw for the Boltzmann equation. You have these two delta functions that correspond to conservation of momentum and energy. But one important difference is that the nonlinearity is cubic instead of quadratic. And of course, this is related to the nonlinear Schrodinger equation being a cubic equation. So this is the kinetic wave equation that comes from the nonlinear Schrodinger equation, but there are also versions for any nonlinear dispersive equation. And there is I've not been completely consistent in distinguishing between the homogeneous and the inhomogeneous context. So here I was presenting the homogeneous context in which everything is invariant by translation and you're on the torus. And then there is no dependence on X, and you should forget about this transport term. So this is sort of a more general setup where there is time dependence involved. And so, as I was saying, this equation was derived first by Pierre, and then rediscovered by a couple of people. Hasselmann, who was a physicist an American physicist in the 50s, working on water waves, and then Zakharov and his group in the Soviet Union in the 70s. But perhaps you have questions. I've been talking much, and I'm sure many things were not clear. So if you have questions, please ask.
So I actually have one. So I guess somehow one thing that one should decide, I mean, for the validity of this equation is a precise relation between lambda, L, and the time scale, right? I mean, all these parameters should be somehow related in a precise way to have this scaling limit. Is that correct?
Indeed, that's a very good point, and I'll be coming to that. That's the analogous of the Boltzmann grad limit, right? Boltzmann grad was fixing a specific relation between the number of particles and the diameter of the particles. So the analogy here is the size of the domain and the nonlinearity parameter, and the time should be scaled correctly. Yes, I'll be coming to that. Thank you.
Okay, thanks.
So here is the analogy with the Boltzmann equation. Maybe I already said that. So particles correspond to phonons or linear waves. The quadratic interaction has become cubic because 3 waves interact in the nonlinearity. The fact that the number of particles goes to infinity corresponds to the size of the domain or the number of relevant frequencies going to infinity. The fact that the epsilon is in a way the nonlinearity parameter. It's telling you how likely it is that the 2 particles will collide, because epsilon is their size. So epsilon going to 0 corresponds to the nonlinearity parameter going to 0. And then we have the same 2 conservation laws. So here is how this would apply to question 1. So question 1 was about the behavior of solutions of the unforced nonlinear Schrodinger equation. So there is a very nice paper by Escobedo and Velázquez who showed that solution of the kinetic wave equation does transport energy to high frequencies like it's supposed to do. So here is a picture that shows how a solution of the kinetic wave equation behaves for large time. So you have 2 conservation laws, the mass and the energy. And so what's happening is that all the mass is gonna focus at 0, and all the energy is gonna be transported to high frequencies. And of course, this is, this has to happen consistently with the conservation of these 2 quantities. So this is what we expect should happen for the nonlinear Schrodinger equation. And so now, if you're able to go from nonlinear Schrodinger to kinetic wave equation, this article of Escobedo and Velázquez solves the problem. As for question 2, there are stationary solutions of the kinetic wave equation, which are called Kolmogorov-Zakharov solutions, and which are just power laws. So rho is just a power of the frequency parameter. And there are a few magical values of alpha, depending on the system you consider. And so the expectation is that this
c'est
power law...
l'équation que tu regardais.
Sorry?
L'équation de Zakharov.
Oui. Yeah. So, sorry, what's the question? Yeah, so what I wanted to say, is there a question? What I wanted to say is that this power law that corresponds to stationary solutions of the kinetic wave equation is expected to be the same as the one you see in the experiment I pictured here. So this slope, in other words, is expected to correspond to stationary solutions of the kinetic wave equation. So it's more complicated than that because experiments show that it's not always the case. And why it's not always the case is unclear. But at least that's in some experiments, it works remarkably well. And the power law you observe is exactly the one coming from the stationary solutions. And so this is, hinting at the fact that the kinetic wave equation, could play a role in understanding this. Unfortunately, there are limitations. First, can you derive the kinetic wave equation from the nonlinear Schrodinger equation? I'll be discussing that in a second. And second, there is a question about swapping limits. Namely, to derive the kinetic wave equation, you need to send epsilon to 0 and lambda to infinity. Or sorry, L to infinity and lambda to 0, sorry. So the domain has to become infinite and the strength of the nonlinearity has to go to 0. That's what you need to derive the kinetic wave equation. And then to answer questions 1 and 2, you need to look at very large time scales. So you need to let t go to infinity. And to which extent this limits commute is, of course, a complicated question. Okay, so yes, now let me come to the rigorous derivation of the equation, and let me present what is known about the validity of this kinetic wave equation. So the microscopic model is the nonlinear Schrodinger equation. There is a small parameter lambda, and that corresponds to weak nonlinearity. And there is a large parameter L that corresponds to infinite volume. And then the effective equation is the kinetic wave equation that I already wrote down, where you have this linear part, Liouville's equation. And then you have the collision operator that is very reminiscent of Boltzmann's equation, except for it being cubic instead of quadratic. And the conjecture put in more mathematically rigorous terms is that you let lambda go to 0, you let the volume go to infinity, and you pick random phases for the data. So you expand the data in Fourier series, and you make sure that the phases of the Fourier coefficients are IID. Then you can make a small computation to see what the right kinetic timescale is, and it should be this timescale, this kinetic timescale. And then the conjecture is that if you take the expectation with respect to the random phases of the Fourier coefficient, and you rescale time properly, what you should see in the limit is a solution rho of the kinetic wave equation. So you is a solution of the nonlinear Schrodinger equation, and rho is a solution of the kinetic wave equation, right? So you should go from this Hamiltonian system to this kinetic model. So that's for the homogeneous case where you can work with Fourier series. In the inhomogeneous case, you need to have slightly more complicated data. You need to have data that maybe it's best to draw a picture. Data that have sort of an envelope around random oscillations, and random oscillations happen on a very small scale, or random fluctuations happen on a very small scale, while the envelope is on scale 1. So there is this scale separation, and then you need to take the Wigner transform in order to get to the solution of the kinetic wave equation. And so the Wigner transform, yeah, that's given by this quadratic expression in U. So that's a bit more complicated. And of course, I should mention here the many works on random Schrodinger, random linear Schrodinger operators, with, of course, important contributions by Spohn, Erdős, Zalmhofer, and Yao, who did also derive kinetic models and then even diffusive models in this linear setup. And many techniques are actually common to the linear and the nonlinear case, but there are also differences. So now I come to state what is currently known. So there has been much activity lately. All of these articles are 1 or 2 year old, and prior to that, close to nothing was known. So let me start with random homogeneous data. Then we now know that it's possible to derive the kinetic wave equation up to a small fraction of the kinetic timescale, which is in a way the best you can hope for. It corresponds to Lanford's result for the Boltzmann equation, and Lanford's result, has not been improved in this respect over the last 50 years. So it's presumably very hard to do better than that. This was achieved by Yu Deng and Zahir Hani in a very remarkable recent paper. And this was following works by Buckmaster, myself, Hani Shatta, and Kolo and myself, where we were falling a bit short of the kinetic timescale. This is what the situation is currently for random inhomogeneous data. Then the kinetic wave equation is valid up to an arbitrarily small power of L that goes to infinity times the kinetic timescale. So you're just falling short of reaching the kinetic timescale, and this we did with Mpatsoglu and Kolo. And there is also a recent paper by Stafilani and Tran, who consider the randomly forced system, and they show that the kinetic wave equation is valid up to a fraction of the kinetic timescale. So these are all, once again, very recent and very, I think, exciting developments in this field. Perhaps you have some questions before I have 5 minutes to say a few words of the proofs, but perhaps you have some questions.
Random homogeneous data, this means random initial data.
Yes, random initial data, and homogeneous is space homogeneous.
So you make the phases of the Fourier coefficients random, or how does it work?
That's right. So either you look at the Fourier series whose coefficients have random phases, or you see it as a Gaussian process that is space invariant on the torus.
Thank you.
Yeah, so just a few words of the proof. So one important idea in this whole business is resonances and nonlinear sense of the term. So you want to solve the nonlinear Schrodinger equation, and we know it's a good idea to expand it in Fourier series, expand the solution in Fourier series, and you can even filter by the linear Schrodinger group, which corresponds to adding ITK squared in the phase. And if you do so, you see that the equation satisfied by the Fourier coefficient is the following. So AK dot, time derivative of AK, is the sum over the Fourier coefficients adding up to 0 of AL, AM bar, AN, e to the 2 pi it omega, where omega is this phase function. And then you have dichotomy between cases where omega is very large, and if omega is very large, then you see that this time oscillations will cancel the effect of the corresponding nonlinear interaction by an averaging effect. And on the other hand, if omega is very small, then you can forget about these time oscillations, and the nonlinear interaction becomes dynamically relevant. So there is this idea that you need to only keep these interactions for which omega, which is known as the resonance modulus, is sufficiently close to 0. And what you see appear here is the two conditions that we have, that frequencies add up to 0 on the one hand, and same thing for their squares up to alternating signs. This is what we refer to as conservation of momentum and energy. So now that's at the level of the nonlinear Schrodinger equation. At the level of the kinetic wave equation, you see that these conditions, that the momenta add up to 0 and the energies add up to 0, is not discrete anymore. It has become continuous, right? There is these delta functions that appear in the integral in the nonlinearity. So a good way to understand this graphically is to realize that omega being equal to 0, that is the squares with alternating signs adding up to 0, means that the frequencies are arranged as a rectangle. And of course, they are on the lattice ZD, or ZD over L. And this is the 2D picture. There is, of course, a higher dimensional analog. So as you let L go to infinity, the lattice, which is ZD over L, which is dual to the torus of size L, becomes more and more refined with a smaller and smaller mesh. And if you try to count rectangles, you see that there is something akin to a density of rectangles that appears. And ultimately, what you need to do to pass through the limit is to show that indeed there is such a density. And of course, this is related to number theoretical problems, because you're on the torus and because you're dealing with sums of squares essentially. And so there are tools that have been developed by number theorists to understand these aspects. So this tells you sort of how to go from the discrete to the continuous limit. But then the next problem is to control the solution and propagate chaos, as the expression goes. That is to say, show that there are not too many correlations developing under the effect of the nonlinear interaction. And this is best achieved by working with diagrams, Feynman diagrams, as was done, for the linear problem by Spohn, Erdős, Samhofer-Yao. But I don't have time to explain this, so I'll stop here and thank you for your attention.
Thank you very much, Pierre, for this very nice and very clear presentation. Do we have any question? So I think I have one. So could you comment on the connection between this kinetic wave equation and the quantum Boltzmann equation? Because I mean, I think of, so I could think of your initial nonlinear Schrodinger equation as already as an effective nonlinear equation for interacting bosons, and for this class of interacting quantum systems, but also for fermions. In fact, there are conjectures about the validity of the quantum Boltzmann equation, which in a certain scaling limit, which looks like the equation you considered, except that if I'm not mistaken, in the right-hand side, you would also have a quadratic term, while here you only have cubic terms on the right-hand side. So is there another scaling limit starting from NLS that would give you quantum Boltzmann, or you, I mean, right, yeah.
So that's a very, very important question. So first, I think what you're saying is very true, that there sort of, in a way, so what you're saying in a way is that first you can take a mean field limit to get NLS from the quantum n-body problem, and then you take a collisional limit to get a kinetic equation from NLS. So there is some truth to that, I think, but it's more at a heuristic level. Indeed, the quantum Boltzmann equation, so one of the many versions that exist, depending if you look at bosons, fermions, etc. The nonlinearity is exactly the sum of the Boltzmann nonlinearity and the kinetic wave equation nonlinearity. So there is the quadratic and the cubic terms. You just add them, and this gives you the nonlinearity of, I think it's the bosonic version, if I'm not mistaken. But yeah, so there is clearly an analogy, and I would be very tempted to say that the methods that we developed can be applied to the quantum n-body problem. But of course, random phase approximation has to be understood differently. But it seems to me it is very linked.
Okay, so you think you think one should really start from the many-body problem to get the quantum Boltzmann? Can't one hope to find another scaling regime in which you can start directly from NLS, or maybe another class of initial data?
Well, yeah, no, I think, I'm not a specialist, but it seems to me that NLS is really the mean field limit. And so you cannot really take successively the mean field limit and the collisional limit, because, well, obviously you lose the quadratic terms, right, in the process.
Okay.
Maybe I'm just being too naive. Maybe there is something more clever that can be done.
Thanks. Other questions?
You mentioned a power law. There was an exponent alpha, and could you explain what values of alpha can one expect and how?
So it depends on the specific physical problem, right? So for instance, much work has been done on water waves. So water on the surface of a fluid, sorry, waves on the surface of a fluid. And then, depending on which regime, it might be gravity waves or capillary waves. And for each of these, you have a specific exponent. So that's for water waves. But the same holds true for plasma waves or ocean waves, or so there are many instances where you can identify an exponent. And the question is, where does it come from? And sometimes it coincides exactly with the prediction from the kinetic wave equation. So the picture is not as clear as the Kolmogorov law, where you have a magic component that works for hydrodynamic turbulence. Here it depends on the specific physics of the system.
And in the case of, I don't know, NLS, is there a specific exponent or?
Okay, so I'm embarrassed to say that I don't know it by heart, but there is one. There is one, and actually, I think there are several possibilities. There are two possibilities depending on whether you have a direct or an inverse cascade, and this has to do with the specifics of the experiment. But then you have two possible exponents alpha, but yeah, I'm ashamed to say I don't know them by heart.
Thank you.
Are there other questions or comments from the audience?
Yes, I would like to thank you very much for this nice talk. And actually, I would like to go back to Marcella's question, relation between mean field limit and the kinetic limit. Is there some kind of intermediate case where you can think about perturbation with respect to the mean field limit?
I'm not sure. Maybe what I can say is that in the classical setup, so for the Boltzmann limit, so Newtonian to kinetic, you can have both effects, right? You can have particles that interact through collisions and through field, right? And then the limit will have a Vlasov part and a Boltzmann part. So one mean field and one collisional term. But this is not really answering your question. I would be tempted to say, that the best is to just try to tackle the full problem. Maybe it's unrealistic. I don't know this problem well, but I would be tempted to say that the methods that we have could say something in this quantum context.
Actually, I do refer to the full problem. So we have an n-body quantum problem. On the first step, you can obtain mean field limit. But then you would like to go beyond the mean field limit and see whether there's intermediate regime from the full n-body problem, but intermediate regime as a perturbation of the mean field limit. But we are talking about full problem.
Yes, but very naively, the mean field limit is enabling particles that are far away to talk together, and the collisional limit is only enabling particles that are at the same position to talk together. So how do you go from one to the other?
Okay, there's also Gross-Pitaevsky limit where actually particles have a short range interactions.
That's okay. That's true. Gross-Pitaevsky, but yeah, okay, that's true. it's sort of degenerate mean field. Okay, basically, I'm not sure, but maybe things can be done.
I'm not sure either. I'm just speculating. Okay. Thank you very much.
Other comments or questions? Okay, so that doesn't seem the case. So let's thank again Pierre for being with us and for the nice presentation.
Thank you.